Sanjay, I'm Aaron, and for our project we did an audio guitar DSP, that's pedal emulation, and that's basically just like a distortion pedal like that you see guitarists use. And for our requirements, we wanted our circuit to actually output the waveform, and we wanted to distort the waveform on several levels. We wanted to echo, so like sort of like a reverb, I think what it's called. And we also wanted to implement a filter that set around 60 Hz to eliminate the hum.
Yeah, and right now only the distortion works, so I'll get to what happened later. So for the hardware part of this, it's pretty much the same thing as the function generator, not the function generator, the temperature sensor with the DAC and the ADC. So the guitar in would come in from a gain offset circuit, so that would be like an op amp that just boosted the gain of the guitar to a range between to 3.3 volts peak to peak, and then that ran through an offset circuit to like get the full range of the ADC. So the guitar was inputted through there, and then it went in to the Nexus board. All the DSP was done in there, and then as of now, it's output directly through the DAC. But so basically, like Aaron said earlier, we were supposed to have a filter in there. And because of like the sampling constraints and the delays in C, we thought like, okay, so it'd be better to implement a filter in hardware. So you can do that by using a user-defined IP core. And what that is you know how you like drag IP cores into the to your system assembly view. You would actually have to write VHDL, import it in as a hardware core, look it up, and then like synthesize it. So we wrote the VHDL for it, and it like when I turned on the speakers, it blew my ears out. I don't know what happened. We wanted to implement a recursive IR filter using a process, top-down logic. Like okay, like there'll be certain delays in the signals, and then that will get multiplied by certain coefficients, and then you get your filter. That it did not work first time around. I guess the coefficients I calculated were all wrong. So speakers just fried, and then I tried some new coefficients that included floating point decimals, and apparently whatever variable I was using in the VHDL didn't work. So it didn't work out in the end. So this, like, I was able to output data through here and then get it back, but it was just unaffected. It just went in and went out. There's no filtering. And anyways, so that's the hardware part. The software, all it was for the distortion. Basically, if you input your signal and clip it at certain levels, it'll introduce additional harmonics into your waveform. So that's the distortion you hear in like rock songs, for example. So the more clipping you have, the more like metal it gets, if you will. And you also need a gain stage, otherwise you'll just get like a flat line eventually. So then if it's like full-on clip, it'll just be lined like a square wave, like a very raspy sounding signal. And now of course there's like a whole bunch more effects you can add to this, like several filters, and there's like all sorts of Butterworth filters and Cheryshev filters, all that stuff, which is beyond me right now, which you can implement to make the signal sound better. And also for the echo did not work, but that was originally, basically we could store the present value into an array and just output it at a certain time. But the code just broke whenever it was implemented. So as of now, it's only distortion at certain levels. So for design, we're of course sampling an audio frequency. The maximum the maximum frequency coming out of the guitar was roughly between 7 to 8K. So of course there's only twice that would be 16K. So it was only necessary to sample at 16K. The board was sampling at 100K hertz right now. It doesn't affect the signal adversely at all. It's just running at that high because we can, and we're not limited by like the timing and the code, so it works. So might as well keep it that high. And like I said before, clipping the waveform introduces harmonics, produces distortion, and then the echo and the filter, there they are, but they didn't work, unfortunately. And then, so for the integration, the switches are what's used to select the various amounts of distortion. So it goes from clean to just like full on metal, if you will. And then like gain is also introduced with each distortion, so it swings the full output. And filter doesn't work yet again. And the two GPIOs are used to interface with the filter. This is the spectrum of just like flailing on the strings, if you will. So you can see like this number. Oops, was I standing in front of the projector this entire time? Oh well. Like by just slamming on the strings, like your maximum frequencies are only below like roughly 2,000 hertz. So, like I said before, it was only necessary to sample it like about 4 times the octave of that, which would be roughly to sample it roughly like 16 kilohertz or something like that. It got all the information fine if we play it. So, I guess demo time. Alright, go ahead. Turn that on. Okay, so if you look at the oscilloscope over there, you can see the waveform coming out of the guitar. So right now it's set to clean, and if you play too loud, it will distort, even though it's on clean, because the output, like the output from this is really variable. Like I measured it to be maximum 60 volts peak to peak, millivolts peak to peak, but you can go beyond that if you strum really hard. So it might distort just because that's the maximum range of the ADC. So it's horribly out of tune, but I won't play anything, I'll just strum. So this is clean. You can see the signal over there. It's not distorted in any way. There are no effects on it right now. It's just in, out, a little bit of amplification. And then if I want to put a slight amount of clipping onto it, if I play hard, you can see how if it goes beyond a certain level, it clips. So it sounds like a 50s crunch, if you will. Then if we go a little more, it sounds more and more like rock and roll-ish. It has a lot of noise in it right now because with the addition of new harmonics, there'll be like crap way beyond 20 kilohertz, which we don't want. A lot of fuzz. So it would be ideal for a bandpass filter to be in there. And then we can go a little more, make it really raspy. So, I'm sorry about that. It's not tuned at all. But like the noise you're hearing right now is just touching it. The pickups will hear me rub against the strings, and then it'll get clipped. So again, there are other filters to get rid of that, but the original filter we had didn't work great. And then there's a final level of distortion, which is just oops. And then you can solo it if you want. All sorts of crap up there. And then it works best in the mid-range because I can't really explain why, but it just works well like in this area and like third or fourth octave of the guitar. Down here it's very noisy. So it's quite noisy down here, but it works well in the mid-range. But that's the basics behind the distortion of the input waveform. Sorry about the noise. And I guess that's it.